The following sounds have been synthesized entirely from scratch. If you would like to hear these soundscapes in full, I've uploaded them to my Bandcamp, linked below. This video is the second part of my ongoing wildlife synthesis series, and I will expand on some of the topics discussed in the first part about insect sounds, so be sure to check that out if you haven't already. In this tutorial, I will focus on frogs and toads, known as Anurans, since they rely on acoustic communication more so than other amphibians, which may primarily use chemical or tactile stimuli instead. There are thousands of Anuran species, so for this video I'll focus on three families: tree frogs, true frogs, and true toads. Now, all of these families belong to the order Anura, so toads are still technically frogs. Still, vocal behavior varies significantly between these families. And before we start, I quickly want to point out that I've uploaded the presets and project file for these sounds on my Patreon, if you'd like to support me. Moving on, we can start by learning how frogs make their calls. Most frogs produce sound by forcing air from their lungs through their vocal cords, and interestingly, we're actually the first land animals with vocal cords. They usually make short bursts of sound at varying rates, referred to as pulsation, which we can replicate by synthesizing individual pulses. Furthermore, frogs possess vocal sacs, which allow them to produce calls repetitively and for longer durations by recycling stored air. It's commonly stated that these vocal sacs act as resonant cavities, but this hypothesis was rejected by research experiments using heliox gas. Thus, I won't be referencing it for my sound design. The vocal system of a frog can be complex and nonlinear, which is to say that the vocal structures might not behave predictably, and the resulting sounds may contain what are called acoustic irregularities, like subharmonics, sidebands, etc. We'll see examples of this later on once we start analyzing frog sounds. Now, to get ideas for some parameters to incorporate into our sound design, let's explore some concepts in bioacoustics. I'll be largely referencing a great book on soundscape ecology for this section, which I mentioned in the previous tutorial. I've linked the book in the description for anyone interested. An organism's physical features shape the sound it produces, but arguably the most obvious feature is body size. This is known as the morphological adaptation hypothesis, and it's been demonstrated that body size has an inverse relationship with the dominant frequency an organism makes. Or put simply, large-bodied animals produce lower frequencies and vice versa. So we can create a parameter for body size in our patches that controls the fundamental frequency. And depending on the organism, we may also map it to other values such as pulse rate, which we will see examples of later. In addition to morphological features, we can start to think about the organism's environment. By researching the habitats they reside in, we can come up with ways to contextualize our soundscapes. With frogs, for example, most of the species diversity is found in wetlands and tropical rainforests. So there's a good chance that you will include geophonic sounds like rain and flowing water alongside noises produced by other animals that live in these environments to accompany your frog sounds. We can also study the acoustics for each habitat and use that research to direct how we apply reverberation and filtering. Because frogs mostly live in wet environments, we can reduce high-frequency content in our soundscapes, as the porous soil and dense vegetation in the environment absorb more sound, and higher frequencies attenuate faster than lower ones due to scattering. However, the surface of water does reflect a good amount of sound, so much so that a sound produced near water can propagate almost twice as far as it would in an empty field. And since frogs often gather at ponds or streams, we can therefore generate a lot of depth in our soundscape, with very distant frogs being audible, but with their signals still noticeably degraded and dampened by the environment. Another environmental factor that influences sound is temperature. As we saw in my insect tutorial, the chirp rates of many insect sounds were related to temperature. And as we will see later on once we start sound designing, the pulse rates of frog calls may also rely on temperature. Furthermore, there is a neat reverb plugin I've mentioned on this channel before, called Room 360, which has a temperature knob allowing you to simulate the effect temperature has on the propagation of sound. I'll link the website below for anyone curious. We should also consider the time of day in which our frog choruses occur, as we could include other noises like insect choruses depending on the time. The last concept I want to cover is the acoustic niche hypothesis. The idea is that different species cannot coexist in the same place and time unless they have different resource requirements. If their needs were identical, they would either limit each other's access to the resource, or one species would outcompete the other. And because many animals rely on acoustic signaling to survive, like any other vital resource, it's important for them to occupy unique acoustic spaces, referred to as acoustic niches, so as to avoid competition with other species. This acoustic space has three primary dimensions in which an animal may partition their signals. The first of which is the spatial dimension, which relates to the animal's location. Then there is the spectral dimension. This refers to the frequency components of the animal's signal. Lastly, there is the temporal dimension, which is about when the animal calls, and can refer to short-term intervals, time of day, or even seasonal timing. As we sound design different animals, learning about how they use these dimensions will help us better understand their calling behaviors. And while this idea of acoustic partitioning will be significant when it comes to creating large biodiverse soundscapes, for this video, it's important to recognize that frogs can adjust their calling behavior so as to stand out among their own species. This means that when we design chorus sounds, we can make each call vary ever so slightly and occur at different intervals. We can also vary the size of animals using the body size parameter mentioned earlier to extend the range of frequency content in our soundscape. But now that we've navigated some of the ideas behind the production of biophonic sounds, we can start to analyze their features. I wrote this section assuming you already understand the topics I discussed in the analysis section of my insect tutorial, so be sure to familiarize yourself with those concepts if you haven't already. Before we look into analysis methods, I want to recommend some places I gather reference sounds. The first is freesound.org, which, as the name suggests, is a large repository of free samples, and there are a lot of wildlife recordings on there. The second source is Cornell University's MacaulayLibrary.org, which is the largest wildlife media resource. And Earth.fm has some great recordings to reference for natural soundscapes. Now, on to analyzing sounds. I talked about measuring pulse rate and pulse amplitude shapes of reference sounds manually in my insect tutorial. However, there is actually a quicker and more automated way to do this for some sounds. I was on a call with my friend Lukasipo while analyzing frog sounds. And when I was observing the pulses, he had the clever idea of using envelope detection, which has the added benefit of extrapolating the low end, which allows us to see the pulse rate. That may be confusing, so let's go through how we can make an envelope detector and how to use it to analyze signals. We can make the envelope detector using the free open source plugin PlugData. We want to load PlugData in as an audio effect, and we can start with the audio input object. Then send the signal to a Hilbert transform object. This object outputs a phase quadrature version of the input signal, which is to say that it outputs the same signal but with a 90-degree phase offset. Now, to get the envelope, we can square both the in-phase signal and the quadrature signal using the power function objects. Then we simply add these signals together and get the square root using the corresponding objects. And to finish the patch, we send the signal to the audio output object. Ideally, the input should be somewhat simple in frequency content, which can be achieved by filtering the input signal with the bandpass or low pass. Now, if we apply this patch to an American toad sound, for example, we can see that the pulse rate, which is now the fundamental frequency, is around 40 Hz. Furthermore, we get a clear picture of how the pulse rate changes over time. If a sound has a pulse rate which is too low to be seen on the spectrum, you can transpose the sound by 12 semitones and divide the fundamental frequency you see on the spectrum by 2 to get the pulse rate. With this being said, I still manually measure the pulse rates at times for more intricate sounds. Going back to the American toad example, we can bounce the track to see the processed waveform, which shows the precise amplitude shapes of each pulse. And again, credit to lukasipo for showing me this helpful technique. Alongside studying pulse shapes, we should also look for irregularities like subharmonics, which are tones that are fractions of the fundamental frequency, and learn how to replicate them. I mentioned earlier how nonlinear mechanisms in the frog's vocal system can give rise to acoustic irregularities. So let's take a look at an example of that. Here is a sound made by an American bullfrog. First, we can see that there are even and odd harmonics. However, because the vocal system is nonlinear, there are also these inharmonic partials between the harmonics. And we can just barely make out a subharmonic as well, which is half of the bass frequency. These tones can be replicated using amplitude modulation. Specifically, we can modulate the amplitude of a saw wave, which contains the integer harmonics the reference sound has, by a sine wave at half of the saw's fundamental frequency. This will create partials that are 1.5 times the fundamental, 2.5 times the fundamental, etc., including a subharmonic at half the fundamental. The reason why this works is fairly straightforward. Let's focus on just the bass frequency, which is a 230 Hz tone. Technically, it changes over time in the reference sound, but we'll ignore that for this example. When we modulate the tone's amplitude by half of this frequency, at 115 Hz, we get sidebands at 345 Hz and 115 Hz, which are simply sum and difference frequencies. And to put it another way, the upper sideband is 1.5 times the fundamental, and the lower sideband is half the fundamental, which are the same relative partials we observed in the reference sound. Sound designing wildlife will require us to be attentive to details like this, so I encourage you to try and be as analytical as you are creative with these sounds. Anyhow, with these topics out of the way, we can finally start making some frog sounds. Like in the previous tutorial about insects, I'll be using phaseplant to sound design the frogs. The first frogs we will synthesize are the hylids, which include tree frogs among other species. Two iconic examples of hylids that we will look at designing are the Pacific tree frog and the spring peeper. Let's start with the Pacific tree frog. This species can produce a variety of sounds, but here are two in particular that I find interesting. The first of which is their diphasic call, which is the classic two-part ribbit sound. The other sound is an aggressive trill used to create spacing between males. We'll include both sounds in one patch, but first let's focus on the diphasic call. We want some frequency content to work with. Here I've made a group for the bass tones based on a reference sound, which include the fundamental starting at 1.9 kHz, a higher tone, and a subharmonic at half the fundamental. We don't have to make a separate wavetable for the subharmonic, as we could make it inside the harmonic editor or with modulation, but sometimes I like to separate it in case I need to control it independently. Next, we want to control the frequency of this group using a macro, and if you recall the relationship between body size and frequency as discussed earlier, we can call this macro size, and make the frequency decrease as the size increases. Now, to create the pulses in the call, we can use audio rate modulation, and start by making the amplitude shapes. To do this, make a wavetable, and delete the envelope module so that it doesn't output sound. Then, click on the waveform editor to begin making the pulse shape. We can analyze the pulse shapes in our reference sound, which we can extract using the plug data patch we made earlier. On frame 1, let's make a shape that looks something like this. And now, because the pulse width changes over time in the reference sound, we'll want to create a wider pulse. While still in the waveform drawing mode, we can click on frame 256 and widen the pulse shape. Let's click Done once we're finished, and now we'll be able to use the frame value to change the pulse width. And for the pulse rate, we can set the wavetable's harmonic to 0 and dial in the pulse rate using the shift value. In my reference sound, it mostly sat around 90 Hz, so we can set the shift value to 90. Now, instead of modulating directly from this wavetable, we can place a mix module after it. This will allow us to mix different pulse wavetables together, which we can use to change the pulse shape over time. We can add one more wavetable where the pulse is slightly offset so that we can mix in a bump to the amplitude shape, which is something I noticed in the reference sound. We can set the level to 0 by default, as we will modulate this later on. Furthermore, make sure the shift values of these two wavetables are identical. Then we can fully modulate the levels of each wavetable in our tone group using the mix module, like so. Now that we have the pulse amplitude shapes, we can start working on the pulse train. To do this, we can use curve modulators. Starting with the amplitude pulse train, here is the curve I made for the diphasic call. We can set the level of the mix module in our pulse amplitude group to 0 and modulate the level with this curve instead. Next, we need to make the frequency curve. Here is the curve I made. We can map this curve to the shift value of each wavetable in our tone group by around 3%. Now, we can use another curve modulator to change the pulse rate of the call over time. In my reference sound, the call starts with a slightly faster pulse rate but quickly decreases to around 90 Hz. So I made this curve to modulate the pulse rate. We can modulate the shift value of our pulse amplitude wavetables with this curve, and do so by around 0.5%. And before we move on to the next step, make sure that the modulator rates are the same, so as not to fall out of sync with each other. Also, to control the frog's calling period using the length of a C3 note as the input, we can set the loop modes to infinite. Next, because we want to implement the aggressive trill into this patch, we should make a control to switch between the diphasic call and the trill. To do this, we can set the depth of our curve modulators to 0% and map a new macro to a remap with this curve. I'll refer to this as the switch remap from now on. We can map the remap to the depth of the curve modulators like so. Now, when our aggression knob passes a threshold, in this case 50%, the curve modulators will do nothing, and thus the diphasic call will not be audible. And to finish making the pulse trains for the diphasic call, we can implement a couple behaviors. First, we can make the pulse width wider on the second part of the call by taking the amplitude pulse train curve and sending it into a remap. The curve we will be remapping it to should look something like this. Essentially, we want a threshold that corresponds to the amplitude level of the second part of the call. We can then use this remap to modulate the frame of the main pulse amplitude wavetable. Next, we can have our bump wavetable increase in amplitude as the call gets louder. We just need to simply map our amplitude pulse train curve to another remap with a somewhat concave curve, and map that remap to the level of the bump wavetable. In my case, I'm modulating the level by about 50%. So far, we've made the pulse amplitude shapes, but we should also make the pulse frequency shapes that are present in each pulse of the reference sound. So let's make a wavetable in a new group, delete the envelope module, and make our curve the same way we did last time, but by replicating the pulse frequency shape instead. Here is the curve I made. And like the amplitude shape, we should also widen the pulse width, which we can do the same way we did before. Also, we should set the pulse rate to be the same as the amplitude pulse rates. Let's create a mix module in case we want to mix in any other pulse shapes later on, and use it to modulate the shift values of each wavetable in the tone group. I modulated them by 20% each. In my reference sound, I observed that the pulse frequency shape was less prominent at the start of the call, so we can set the level of the mix module to 0%, and modulate it using the concave remap we made earlier. I set my modulation amount to be around 100%. At this point, we have a fairly convincing diphasic call. Something I tried that helped it sound a little less artificial was to diffuse the subharmonic a bit using a convolution reverb in multipass. I recommend trying out different impulse responses and seeing which one sounds best to you. On to the aggressive trill, we could start by setting up the pulse shapes. We want to first disable the pulse shapes for the diphasic call when the trill occurs. There are a few ways you could do it, but I simply just made a curve modulator that constantly sits at 100% and mapped it to the levels of each pulse wavetable for the diphasic call by -200% each. Then we can take the switch remap and map it to the depth of this curve modulator by -100%. On to the trill pulse shapes, let's start with the amplitude shapes. We can make two wavetables in our pulse amplitude group for slightly different pulse shapes. Here are the waveforms I made for each one. The trill's pulse rate is slower than the diphasic call, and we will set the base pulse rate to be 32 Hz. For the frequency shape, we can make a new wavetable in the pulse frequency group. Here is the waveform I made. And let's set the pulse rate to also be 32 Hz. Onto the trill pulse train, let's first make the amplitude curve using a curve modulator. Here is the curve I made. We can map the modulator to the mix levels of our pulse groups, like so. And we can map the switch modulator to the depth of this curve modulator by -100%. The frequency of the trill gradually increases over time, so let's replicate this with another curve modulator. Here is the curve I used. We can map this curve to the shift values of each wavetable in the tone group and do so by roughly 3% each. Finally, we can make one more curve modulator to control some other parameters, which I'll just refer to as the control curve. For this, I duplicated the trill amplitude curve but made a few adjustments. Here is the curve. Because the pulse rate in the trill increases slightly over time, we can map the control curve to the shift values of each trill pulse wavetable and do so by the same amount of 0.2% each. We can also map the control curve to the level of the subharmonic by roughly 15%. Let's set the level of the trill's pulse frequency wavetable to 0% and map the control curve to the level by plus 130%. Next, we want the pulse amplitude shape of the trill to change slightly over time. So, set the levels of the trill's pulse amplitude wavetables to 0%. Now, map the control curve to the level of the second pulse wavetable by 50%. Then, map the control curve to the level of the first pulse wavetable by around -90%. And make sure for the control curve itself, like the other trill curve modulators, that the depth is being modulated by -100% via the switch remap. Also, check to make sure the modulator rate is the same for all trill curve modulators, and that the loop mode is set to infinite for each one. Finally, to polish off this sound, let's create some organic variations. We can do so using random modulators and mapping them to various parameters, such as the wavetable frequencies in the tone group, the phase of our pulse shape wavetables, the modulator rates of our pulse train curves, the depth of our pulse train curves, and more. Just make sure when you randomly modulate parameters like phase or modulator rates that the rates do not fall out of sync with one another. So we now finally have some of the individual Pacific tree frog sounds. I'll cover the system I use for building frog choruses later in the video, but for now, let's move on to the next hyalid frog, the spring peeper. Like the Pacific tree frog, the spring peeper also has both an advertisement call and an aggressive trill. So we will approach the synthesis process in a similar manner. Let's start with the advertisement call, which is a fairly simple bird-like chirp. For the bass timbre of the sound, we really only need to use one wavetable. The sound is fairly close to being a pure tone, but there are a couple of quiet harmonics including a subharmonic, which we can replicate using the harmonic editor, like so. And because we're using the first harmonic as the subharmonic, and the second harmonic as the fundamental, we will need to set the frequency of the wavetable to be half that of the sound we're referencing. I've set mine to be 1.4 kHz. Next, we can implement a body size parameter. We can modulate the shift value of the wavetable using this parameter by around -6%. And since we want the ability to switch between the advertisement call and the trill, let's set up the macro for that now. We can make 2 remaps with these curves, and send the macro into both of them. I'll refer to these as the advertisement and trill remaps respectively. We don't need to map these to anything yet, so let's move on to the pulses for now. For the pulse amplitude shapes, let's make a new group with 2 wavetables and a mix module. We will use the first wavetable to create the main pulse shape. We want to control the pulse width with the same method we used in the last patch, so here are the waveforms I've made at frame 1 and frame 256. And for the second wavetable, let's make a transient waveform that we will be able to mix into the main pulse shape. Here is the pulse shape I made for frame 1, and for frame 256 we can make an empty waveform. This is because we'll make a macro to control the level of the transient wavetable, but we want the wavetable to not output anything once we switch to the aggressive trill. So let's first set the level of the transient wavetable to 0, and modulate it with a new macro. And now let's map the trill remap to the transient wavetable's frame value, up to frame 256. Furthermore, let's set the main pulse wavetable's level to 0, and modulate it using the advertisement remap by 100%. Also, different spring peeper recordings I referenced had different pulse widths. So let's use another macro to control the pulse width of the wavetable by modulating the frame value. Let's then set the harmonic value of each wavetable to 0 and set the pulse rate to around 1.2 Hz using the shift value. And because spring peeper calling rates increase during warmer temperatures, we can make a new macro called temperature and use it to modulate the shift value of each wavetable by a very subtle amount, between 0.01 and 0.05. Of course, make sure they are being modulated by the same amount so they don't fall out of sync with each other. To finish the amplitude pulses, let's fully map the mix to the level of the tone wavetable. Onto the pulse frequency shapes, we can make another group with a setup similar to the pulse amplitude group, but with only one wavetable. Here are the waveforms I've made for the wavetable at frame 1 and frame 256. Let's set the level of this wavetable to 0% and modulate the level using the advertisement remap by 100%. We can also fully map the pulse width parameter to the frame value of this wavetable. For the pulse rate, we can use the same exact values and modulation as the amplitude pulse shapes. Now, let's make a macro to control the amount of frequency modulation in the call. To do this, simply set the mix module's level to 0 and map a new macro to the level. Then, map the mix module to the shift value of the tone wavetable. I did so by roughly 17%. That just about does it for the advertisement call, so let's move on to the trill. Let's start by making the trill's pulse amplitude shape. We can do this by making a new wavetable inside of our pulse amplitude group. Here are the waveforms I've made for frame 1 and frame 256. We can then map the pulse width macro to the wavetable frame value. However, I recommend not modulating it fully, since we will also want the pulse width to change over time. Let's set the level of the wavetable to 0% and modulate the level by 130% using the trill remap. For the pulse rate, set the harmonic to 0 and set the shift value to 16 Hz. And because the pulse amplitude shape is similar to the pulse frequency shape in the trill, we can map this wavetable to the shift value of the tone wavetable by around 10%. Now, to create the trill pulse train, we can use curve modulators. Here are the curves I made for the trill's amplitude and frequency shape. Let's set the depth of both curve modulators to 0% and modulate both of them by 100% using the trill remap. Now, put a gain effect in lane 1 and switch it to the percentage mode. Set it to 0% and modulate the gain percentage using the advertisement remap by 50%. Next, let's also modulate the gain percentage by 50% using the amplitude curve modulator. We can now also modulate the frame value on the trill wavetable using the amplitude curve modulator. I did so by around 200 frames. As for the frequency curve modulator, let's map it to the shift value of the tone wavetable by around 2.5%. And before moving on to the last step, check to make sure that the curve modulator rates are identical, and that the loop modes are set to infinite. Finally, like we did with the Pacific tree frog, we can finish this patch by using random modulation on various parameters to create organic variations. And that about does it for these tree frog sounds. I highly recommend experimenting with different pulse shapes and post-processing to get your desired sound. But for now, we can move on to synthesizing the sounds of true frogs. The true frogs I will cover in this video are the green frog and the common frog. Starting with green frogs, let's work on synthesizing their short guttural calls. We can begin the patch by creating a group with 2 wavetables. We will only use 1 frame in each wavetable, and we can create the waveforms using the harmonic editor. The first wavetable will be for the first 3 harmonics, and the second wavetable will be for the high end. They are separate as we will control them independently later on. Here are the waveforms I made for each wavetable. Next, let's make our body size macro now and map it to the master pitch by around -5%. We are using the master pitch to control the call's frequency, since we will want to modulate the frequencies of these wavetables and those of other wavetables by the same amount. I've also set the base master pitch to have an increase of 75 cents. Next, we can filter our wavetables like so. Like the bullfrog example discussed earlier in the analysis section, we can use the amplitude modulation to replicate the inharmonic partials in the green frog's call. Let's make a new group with 3 sine waves, and delete the envelope module so no sound is outputted. These will be our modulators, and we can set the harmonic values like so. We can use the first sine to modulate the level of our tone wavetables by around 95% each. We can also map it to the phase value of the first wavetable by around 50% to shape the tonality a bit. To get more inharmonicity, let's map the second sine to the level of the first tone wavetable by around 25%. And map the third sine to the level of both wavetables by around 20 to 30%. Next, to replicate the amplitude shape of the call, we can use a simple curve modulator. Here's the curve I made. Let's drag the gain of the tone group all the way down and map the curve to the gain by 75%. Now, let's do the same thing but for the frequency shape of the call. Here is the curve I made. Let's map this curve to the master pitch by around 12 semitones. Furthermore, to create a clickier transient, we can duplicate this curve modulator and remake the curve to be a short spike. Let's map it to the master pitch by around 24 semitones. Also, make sure the curve settings are the same for both the frequency and amplitude curves. Next, let's make each call have a unique pitch. Make a random modulator and send it into a sample and hold. Now, let's map the sample and hold to the master pitch by around 2 semitones. At this point, we can begin to shape the sound with effects. This is where you can get more experimental, and I recommend you try out your own techniques and see what works. Still, I'll quickly go over some of the processing in my patch. To start, I'm remapping the sample and hold and using it to modulate the pump and sustain values of a transient shaper. Next, I have a snap heap instance, which is essentially just some randomly modulated formant filters and a frequency shifter. Following the snap heap is just a couple filters. And finally, I have another snap heap instance with some simple processing. To polish off the patch as usual, I'm randomly modulating different parameters to create natural sounding variations. As a side note, while this patch is fairly convincing in a larger soundscape, I still think there are improvements to be made, particularly with the high end. With that being said, we can move on to common frogs, and more specifically, the deep croaking sound they produce. Instead of starting with a wavetable this time around, we will use a noise generator. Let's set the noise to be key tracked and tune it like so. Next, we can filter the noise to introduce these resonances. We can use a new macro as our body size parameter and map it to the semi-cent tuning value of the noise generator by around -50%. Furthermore, we should map this macro to the cutoff frequencies of our filters, alongside other parameters like this. So far, it sounds kind of like wind, so let's start making the pulse shape. To do this, let's make a wavetable in a new group, and replace the envelope module with a mix module. Inside the wavetable editor, we can make our pulse shape at frame 1 and widen it at frame 256. Here are the shapes I've made. Next, let's set the pulse rate to be around 30 Hz. And because an increase in body size is often followed by a reduced pulse rate in frogs, we can map the body size macro to the shift value by around -0.6%. Then we can simply use the mix module to fully modulate the level of the noise generator. Now that we have our pulse shape, let's work on the pulse train. We will use curve modulators as usual for this, and we can start with the amplitude curve. Here is the curve I made. Let's set the level of the mix module in our pulse group to 0, and modulate it with this curve by around 130%. We can also lower the pulse wavetable's level and modulate it with this curve for extra effect. To change the pulse width over time, let's map the amplitude curve to the frame value of the wavetable, like so. In my reference sound, I noticed the croak getting deeper over time. So, we can also map this curve to the cutoff value of the bandpass filter in our noise group by around -8%. Moving on, we can make a new curve to modulate the pulse rate over time. For this, I duplicated the amplitude curve modulator and made this curve instead. Now, let's map it to the shift value of the pulse wavetable by around 3%. In my reference sound, I noticed that sometimes the pulse shape was accompanied by a little bump. So let's make a subtle bump to mix in with our main pulse wavetable. We can do this by duplicating the pulse wavetable and making a new waveform at frame 1. Here is the shape I made. Now, we can send a random modulator into a remap with this curve, remove the modulation from the amplitude curve on our bump wavetable, and map the remap to the level of the bump wavetable by 200%. So far, we have the main behavior of the sound. Now, let's make it sound more vocal with processing. Again, we can be more experimental here, but I'll still briefly go over the effects I'm using. First, I have a formant filter being randomly modulated. Then, I have a convolution reverb with this vocal-like impulse response, where the mix is being modulated by an LFO. Following that is a simple EQ to filter out some high-end. And at last, I have 2 filter tables to introduce more interesting resonances and behavior to the sound. And like the previous patches, I'm finalizing this patch with random modulation on various parameters to produce variations in the sound. With these patches complete, we can move on to the last family I will cover in this video, the family of true toads. The toads we'll sound design in this video are the American toad and the cane toad. The calls they produce have more obvious pulse rates and are noticeably longer than the other calls covered so far. Let's start by synthesizing the American toad's trill. We can begin by creating a sine wave around 1800 Hz. Also, let's place a nonlinear filter after the sine with these settings. For now, it won't make any noticeable difference to the signal, but it will introduce harmonics to the call once we modulate some parameters later on. Next, let's make our body size macro, and map it to the shift value of the sine by around -4%. Now, we can make the call's pulse shape by making a new group with a wavetable and replacing the envelope module with the mix module. Let's make the pulse shape in the wavetable editor. Here is the waveform I made. We can set the harmonic to 0 and set the pulse rate to be around 35 Hz using the shift value. For the pulse frequency shape, let's modulate the shift value of our sine wave using the pulse wavetable by around 30%. And for the amplitude shape, let's modulate the level of the sine wave using the mix module by 200%. We're using the mix module as we will want to mix in another pulse shape later on. As the body size of an American toad increases, the pulse rate decreases. So we can map our size macro to the shift value of the pulse wavetable by around -0.3%. Furthermore, the pulse rate doubles with a 10°C increase in body temperature. So we can make a new macro called temperature and map it to the shift value of the pulse wavetable by 2%, or whatever percent doubles the shift value you've set. Next, let's work on the pulse train shapes. Starting with the amplitude shape, we can make a simple curve modulator with this shape. Let's set the rate to 7 seconds, and the loop mode to infinite. And because an increase in body size also corresponds to an increased call length, we can map the size macro to the rate by around 6%. Now, let's put a gain effect in lane 1, switch it to the percent mode, and set it to 0%. Then, let's modulate the percentage amount with the curve modulator by around 40%. Next, we can make a new curve modulator to make the call louder at the beginning. We will do this in a new modulator instead of our existing one so that it's easier to control independently. To do this, let's duplicate the existing curve modulator to copy the settings, and make a curve like this. Then we can simply map it to the gain by around 15%. Onto the pulse train frequency shape, we can first make the start of the call ramp up in frequency. Let's duplicate our new curve modulator and reshape the curve a bit to something like this. Now, let's map it to the shift value of the sine wave by around -3%. When analyzing some recordings of the call, I noticed that the pulse rate slightly decreased over time. So we can duplicate this curve modulator and reshape the curve by dragging the first node down and curving the slope inwards. Now we can just map it to the shift value of the pulse wavetable by around -0.5%. Next, we can mix a subtle waveform into our main pulse shape. To do this, let's duplicate the pulse wavetable and replace the curve in the new wavetable with a curve like this. Then set the level to 0% and randomly modulate the level however you see fit. Now, to introduce overtones with some subtle behavior, we can use that nonlinear filter we created earlier. First, let's make a noise generator in a new group and delete the envelope module so that it doesn't output sound. Next, let's bandpass this noise. We will use the cutoff of this filter to control how chaotic our modulation is. Let's now duplicate the main pulse wavetable and drag the duplicated wavetable into our noise group after the filter. We can then offset the wavetable's phase by around -100 degrees. Next, let's modulate the phase of the wavetable using the filtered noise by around 50 degrees. Now, as we can see, adjusting the filter's cutoff allows us to control how chaotic the wavetable is. Let's now map this wavetable to the drive of the nonlinear filter by 100%. This gives us a way to create and control interesting overtones in the call. And we can mess with the cutoff of the nonlinear filter alongside the cutoff of the bandpass noise to get different behaviors. In my patch, I kept it fairly subtle by setting the bandpass cutoff to around 750 Hz and the nonlinear filter's cutoff to around 600 Hz. We can finish this distortion by creating a shaper in the effects section. Here is the shaper setup I used. To polish the sound, we can of course use subtle random modulation on various parameters, such as the frequency of the call, the pulse shape levels, and more. And with the American Toad's trill complete, we can finally move on to the last frog we will be synthesizing in this video, the cane toad. This deep call is my personal favorite out of the ones covered, as I find it the most relaxing to listen to. Furthermore, it'll be fairly simple to create compared to the other calls. Let's start by making a group with these signs. The tonality of this call is honestly a little strange, and you could achieve a similar sound using modulation on just one sign as well. Next, let's make a macro for body size as usual and map it to the shift values of each sign by around -5% each. And before we move on to the pulse shapes, let's place a nonlinear all-pass filter after the fundamental. We can make a macro called tone and map it to the cutoff and drive values of the nonlinear filter. This will allow us to shape the tonality of the call a bit if we want to. Moving on to making the pulse shapes, let's start by creating a wavetable in a new group for the amplitude shapes. We'll replace the envelope module with the mix module, and open the wavetable editor to create the amplitude curve. Here is the curve I made. Let's dial in the pulse rate by setting the harmonic to 0 and the shift value to around 16 Hz. And because larger cane toads have a reduced pulse rate, we can map the size macro to the shift value by around -0.1%. Next, let's mix in another pulse shape by duplicating the pulse wavetable and making a new bumpy and offset curve. Here is the curve I made. We can make the level of this new pulse around half that of our main pulse wavetable. Now we can just map the mix module to the levels of our signs by 200% each. To create the pulse frequency shapes, we can duplicate our main pulse wavetable and drag it below the mix module. Let's open the editor and remake the shape. Here is the curve I made. Now let's simply map this wavetable to the shift values of each sign by around 30% each. With the pulse shapes out of the way, let's work on the pulse trains. Starting with the amplitude pulse train, as usual, let's use a curve modulator. Here is the curve I made. Let's set the rate to around 10 seconds, and the loop mode to infinite. We can insert a gain effect, switch it to percent mode, and set it to 0%. Let's now map the amplitude curve to the gain by around 50%. For the pulse train's frequency curve, we can duplicate the amplitude curve and create a long attack for the new curve. Let's then map this frequency curve to the shift values of our signs by around 1.5% each. Furthermore, if you want to give the call some additional behavior, we can mix in a couple of new bump wavetables, set their levels to 0, and modulate the levels using the frequency curve. And to finalize the sound, we can again use random modulation on various parameters to create variations in the call. And with that, we've covered all of the frog sounds in this video. Now, we can start to really bring these sounds to life by creating a chorus system. The chorus systems we build for different frog species will likely differ from one another, but there are some general parameters we'll want to implement. First, we should have generalized parameters in the system that control the parameters we've created in our frog patches, such as body size, pulse rate, and more. The ranges of these parameters, or how unique each individual frog is, will depend on your mapping setup. Next, we should have some parameters to control the acoustics, such as the amount of reverberation, the type of reverberation, damping, and more. In my system, I simplified this by creating two parameters to mix between an observer close to the frogs and a distant observer. And lastly, we want a parameter to control how many frogs are in the chorus, which we can call the density parameter. Furthermore, we will want to try and maximize the chorus density while minimizing the CPU intensity, so that we can generate a convincing soundscape in real time. To create the chorus systems, I used Ableton racks. Let's walk through the rack setup. First, we set up most of the patches such that we can use a legato note as the input. So, we can first create a MIDI clip with a legato note, which defines the length of the chorus. Next, instead of having a new instance of phase plant to generate each individual in the chorus, we can optimize the chorus by creating two chains, one for generation and the other for audio routing. Inside the generation chain, we can use another rack with a few parallel chains, each being a unique instance of our frog patch. If you've already created a fair bit of variations in each patch using random modulation, then they should already sound a little different from one another. We can make each instance start at different times using note delays. Also, we can map our patch parameters to the rack macros, and vary the ranges to emulate some acoustic partitioning alongside morphological variations. We can mute the generation group as we will only want the routing chains to output sound. Now, inside the routing chain, we can insert another rack, and each chain inside this rack will represent an individual frog. We can start by creating the same amount of chains as in the generation group. We will send the audio from the first patch to the first chain, the second patch to the second chain, and so on. To do this, we can use the gate stock plugin. To route the audio, toggle on the external sidechain, get the source by selecting the track the chorus rack is on, and find the corresponding chain the patch is in, and select the post effects of that chain. Now, simply click on the headphone icon to only output the sidechain input. Now, we can put effects after the gate to emulate the position of our frog, such as the FreeMax device ml.distance. Whether you want to put reverb inside each chain or at the end of the entire routing chain, or both, is up to you. I recommend using a mix of convolution and algorithmic reverb to create convincing acoustics. For convolution, some of the outdoor impulse responses by Boom Library are pretty good. And once you start to create more routing chains than generation chains to increase the density, you can avoid repetition by delaying each routing chain differently, and doing some subtle processing in each one, like frequency shifting. To control the acoustics, we can map a macro to various parameters such as the distance or reverb parameters. And to control the chorus density, we can map a macro to the levels of the routing chains. If you don't want to map the macro to each chain linearly, you can send the macro to a shaper, which you can then map to the levels. To polish the soundscape, you can of course add accompanying sounds like wind, rain, flowing water, insects, etc. You can also research which frog species produce choruses in the same place and time, and combine your synthesized choruses accordingly. And at last, that covers all of the information I wanted to explore in this video. But before we go, I have some final comments. That was a lot of information to absorb, and I created this video to be used as a resource to come back to whenever you need to. If you found any of my explanations verbose or confusing, feel free to let me know in the comments and I'll try to clarify it more. I do all of the sound design, 3D visuals, editing, music, and research for these videos, with the exception of my friend Lucas providing some additional music for this series. So if you wish to support the work I'm doing here, you can do so on my Patreon. I've uploaded my frog choruses and presets there, alongside other things like insects, rain, song breakdowns, and more. But at last, that's all for now. The next installment of this series will be about birds, so if you enjoyed this video, be on the lookout for that. Thanks for watching.